Okay, so I have started the recording. So we stopped here. I hope I am audible. If the voice is feeble, let me know. We are talking about the speed up from pipelining. So we already saw this. We said that the speed up from pipelining is equal to the pipeline depth. So this is what we actually saw when we were talking about when we actually first introduced the pipeline. We said that the speed up is equal to the pipeline depth. If there are five stages, what is the pipeline stage? Pipeline depth. Pipeline depth is nothing but the number of stages in the pipeline. So if there are five stages in the pipeline, then then the speed up is five. If there are six stages in the pipeline, assuming that every stage is balanced, there are no stalls and nothing, then the speed up is six. Right? So why should it be balanced? Because if it is not balanced, then the one that dictates the speed up is equal to the stage which has the highest amount of time taking. Right? Let's say there are six stages in the pipeline. Five stages are taking 1 day and the other stage is taking 2 days. Then it is no way that you will get the speed up as six. Right. So if there is a balanced pipeline, which means that each stage is taking equal exactly the same amount of time, the speed up is equal to the pipeline depth. So with this, we already saw when we introduced pipelining, and we said what is this, so we are just looking at it from a different angle, just trying to write some formulas. So what are we saying with speed up from pipelining is the average instruction time unpipelined by average instruction time pipeline. Speed up is nothing but the old time by new time. So what is the old time? The old time, when I'm talking about old time, I am talking about an unpipelined processor. So that's what I'm trying to calculate with the speed up with respect to an unpipelined processor. So the average instruction time unpipelined. So if one instruction was taking, so this example we already saw, one instruction was taking 5 cycles. If one instruction was taking 5 cycles, and we divided these 5 cycles into 5 stages of the pipeline. So we divided it into 5 stages. So here, this is an unpipelined processor. So the average instruction time is 5 cycles. If I divide it into 5 stages, if I ignore the pipeline startup time because it's very minimal, that is for the first for the first 4 cycles, I will not get any instruction out. After 4 cycles, I will get one instruction out every one clock cycle, which means that the average instruction time for an instruction for a pipeline processor is 1. So this is what it is. So it is 5 divided by 1. So the speed up is 5. But I can write the average instruction time unpipelined as CPI unpipelined into clock cycle time unpipelined. What do I mean by CPI? CPI is clock cycles per instruction. So how many clock cycles does it take per instruction into a clock cycle time? Because I know that when I divide something like this, I also want to know what is if I say this is 1 cycle, I want to know in absolute terms in time how much it is. Is it 1 nanosecond? Is it 2 nanosecond? And things like that. Because I am now talking about time. So it's CPI unpipelined into clock cycle time unpipelined. CPI is clock cycles per instruction. So this is one of the formulas that I come up with. Right? And so now I am trying to fill up this. What does this mean? So CPI unpipelined is nothing but so what is CPI unpipelined? So now how many clock cycles per instruction, right? So how many clock cycles per instruction? Here in this case, it's equal to the pipeline depth. So the clock cycles per instruction for an unpipelined processor is the pipeline depth. The clock cycles per instruction for a pipeline processor, if there were no stalls, if there was nothing, then it is just 1 because you are able to get one instruction every clock cycle. But there will be pipeline stalls, there will be pipeline stalls per instruction. So I'm per instruction on average, how many clock cycles are wasted because of the stalls. So the CPI pipeline is 1 plus pipeline stall clock cycles per instruction. So final formula is speed up is pipeline depth divided by 1 plus pipeline stall cycles per instruction. So if there is one stall per instruction, then the speed up is no longer 5 or no longer x, but it is x by 2. Right, because this becomes 1 plus 1, so it's 2. This you already saw. What do I mean by one stall per instruction? Maybe you already saw that if I have a pipeline which is 2 cycles, the other stages are 1 cycle, then you are able to get one instruction every 2 clock cycles. which means that the speed up is no longer 5. The speed up you already figured out that it was 2.5 because I have reduced the speed up by half, because the speed up reduces by half. So what is the speed up? Speed up is again pipeline depth divided by 1 plus pipeline stall cycles per instruction. Of course, it doesn't mean that if I say the stall cycles per instruction is zero point 0.3, there is nothing called 0.3 cycles. It just means that on average per instruction, I'm able to see that there is 0.3 clock cycles, stall cycles per instruction. Right. So if I have seen 10 instructions, then there are 3 stalls in the 10 instructions on average. So that's why it's 0.3. So that's how I calculate this formula. So I am more worried about what happens if there are branches. So we were studying about the branches, and we were studying about what is the issue with stalls. We can clearly figure out that if the stalls are there even 50% of the time, then my performance reduces drastically. So which means that I should not have stalls. The pipeline stall cycles from branches is nothing but branch frequency into branch penalty. So what is the frequency of branches, which means that how many branches do I see? How many branches, what is the average number of branches do I see per program, right? So that is the branch frequency. If I give you 100 instructions to execute, how many branch instructions do you see in that 100 instructions is branch frequency. This is not the assembly code. Please be sure, please try to understand the difference. This is not the assembly code. If there are 100 instructions, and there's only one branch instruction, then branch frequency is not 0.01. Can you tell me why? Please wake up. I know it is 9:20, but please wake up. Ask somebody to give a coffee, or maybe go ahead and make yourself a cup of coffee. But please wake up. Please answer this question. If there are 100 instructions, and there is one branch instruction, just one branch instruction that you see in the code, the branch frequency is not 0.01. Can you tell me why?
Because that branch instruction may be executed a million times.
Yeah, because the branch
Or
instruction, yes, right. So the branch instruction may be executed a million times, right? So we are not talking about the frequency of appearance of those instructions. The processor is all worried about, if I execute 1 million instructions, among those 1 million instructions, how many branch instructions am I executing? Whether it is the same branch I'm executing, whether I'm executing a different branch, it does not matter. If I'm executing the same branch, then I'm lucky because I can do a better prediction. If I'm executing multiple different branches, then my prediction might go haywire. So this is all it depends on how you build the predictor. But branch frequency is the how many branch instructions the processor or the pipeline sees as part of its execution. So that is the branch frequency. And the branch penalty is on average for a branch, how much penalty are you paying? If there was no prediction, then I'm paying a penalty of 1 cycle. If there is some prediction, maybe I'm paying a penalty of 0.5, 0.3, 0.2. It depends on the prediction accuracy and how the workload behaves. Right. So the pipeline stall cycles just from the branches is branch frequency into branch penalty. I can plug this here. I can plug this here and say the speed up is pipeline depth divided by 1 plus branch frequency into branch penalty. Can you guess how many what will be in general, if I take any workload, what will be the branch frequency? So you are so you are saying Intel, you are designing a processor, you want to figure out what is the branch frequency, which means that you don't know the workload, what the user will be. There will be a set of workloads, generic, there will be a set range of workloads. In general, on average, what will be the branch frequency? Do you think it will be 5%, 10%, 100%? Yeah, any answer is fine.
So 60 to 70%.
Any other answer?
40 to 50%.
Yeah, just try to read about it. Maybe I will not tell the answer. Just try to figure out on average, what is the branch frequency, right? So let's say, I'm not saying that's the right answer. Let's say it's 50%, right? So if the branch frequency is 50%, it's 0.5. And if I'm adding 1 cycle every time, if I say, let's say I'm paying a penalty of 1 cycle every time, then the speed up is pipeline depth divided by 1 plus 0.5 into 1. So which is 1.5, total will be 1.5. So pipeline depth divided by 1.5. So 5 divided by 1.5, that will be your speed up. So it will no longer be 5, but it will be some other number, which is between 2.5 and 5, which means that I am losing out on performance if I don't build a predictor. So the way to reduce is either I have to reduce the branch frequency, which is not in my hands because the branch frequency is dictated by the program behavior, and I am not the guy who is writing the program. Somebody else is writing the program. So I can't reduce the branch frequency. Of course, compilers are intelligent enough to maybe reduce branch frequencies, but in general, as a hardware, I'm not able to reduce the branch frequency. The only way I can reduce something is by reducing the branch penalty. Because this is a linear function, I will still get speed up higher. Right? I can reduce branch frequency. We already saw this in the first class of computer organization. We saw we can reduce branch frequency by doing something where I took a for loop and did something else for that for loop. What was that? So maybe you might not remember it. There's a thing called loop unrolling that we did. We said that, okay, the same instruction is just copy pasted 4 times instead of, so we had a for loop, right? So that is one way to do it, but there are disadvantages to do it, but that you will understand maybe later in the course. Without that, I hope you have understood these formulas. If you haven't understood, please answer the poll. We'll go to the next topic in the class. Wake up, please wake up. Arey, wake up, yeah. Okay, you're not taking the poll, so I am 100% sure that you're not even listening to it. Okay. Anyway, I'll take attendance again so that you will get. Okay. So we were seeing, so we'll formally introduce. So we have been seeing stalls. We have been seeing what causes a stall. We said that, okay, I have an instruction like this. If I have an instruction, let's say add R1, R2, R3, and subtract R4, R1, R5. There is a dependency between these two instructions. There is a dependency between these two instructions. So we said that this will result in a stall, but maybe not in the stall because I have something called forwarding. But we hadn't formally introduced what is a stall or what is the dependency and things like that, right? So now we'll try to formally introduce you. What is the okay. See, let's say we have we are talking about branch frequency. All right, so let's say I have an instruction like this. I have add R1, R2, R3, and then subtract say R4, R5, R6, and then I have jump not equal to so label, some label, right? And this is the label. So let's say I have this piece of code. If I just look at this piece of code, there is one instruction which is branch. So there is just one of this instruction which is a branch. Of course, this is end. Okay, maybe I should not do this. Let's say there are maybe 1,000 instructions before this loop. And then followed by another 1,000 instructions. Okay. So there are 1,000 instructions before this and 1,000 instructions before this, and there is this loop, right? So if I just look at how many branch instructions, let's say all these instructions that I'm talking about are not branch instructions, they are just arithmetic instructions. Let's take they are just arithmetic instructions, or they are doing some kind of load and store. So the total number of instructions in this entire thing is 2003. Right, because there are 1,000 plus 1,000 plus 3, that is 2003 instructions are there in this piece of code that I gave you. If I ask you what is the number of times you saw a branch instruction, if I as a programmer, if I give you this piece of code and you as a programmer saw, if you as a programmer saw this entire piece of code, you try to figure out how many times there is this branch frequency, how many times did you see, what is the ratio that you saw that there is a branch instruction, you will easily say that it is 1 divided by 2003, because you saw only one instruction, which is a branch, among the 2003 instructions. So it's like counting the number of words counting the number of words which say hello, right? in a text that I gave you. If I ask you to find out the number of times hello is called, you will just count the number of hellos, and you will say that the hello frequency is the number of times you saw hello and the total number of words. So that is the branch frequency that you would say. But this is a wrong way to do it, because I am not worried about how many times you as a programmer saw that branch instruction. I am more worried about as a pipeline, how many times did I see this branch instruction? And that is dependent on, because I can go on and on, right? So I come to this label, I again jump, right? And then I come here, which means that I'm executing this branch instruction the second time. Then again, I go and I execute this the third time. I can again go and I can execute this time. Let's say this entire branch is executed 1 million times, right? So if it is executed 1 million times, then I'm not worried about this 1000 instruction. I'm not worried about this 1000 instruction, because what is the total? So let's say if this total branch is executed, if this entire branch structure is executed 1 million times, let's say this entire branch structure is executed 1 million times, right? So for some reason it is executed 1 million times. So which means that the total instructions for the compiler executed, sorry, the total instructions the pipeline executed for this entire stream is 1 million plus 2000 instructions. Because these executed only once, I can easily forget this because this is a pretty huge number. So this was executed. Okay, so did I do something? Sorry, this is 3 million. Because this loop was executing 1 million times, which means that this was executed 1 million times, this was executed 1 million times, this was executed 1 million times. This is still 1000 times, this is still 1000 times. So the total number of instructions that the pipeline executed is 3 million plus 2000. So since 3 million is a huge number, I will anyway forget this. Among the 3 million instructions this pipeline saw for this instruction stream, 1 million is branch. So the branch frequency is 1 by 3. So the branch frequency, I can easily say that it's 0.33, right? So that is the branch frequency. So how many times do I see the branch instructions? So that is the branch frequency. Right? So this is, let's say for this example, it is 0.33. And let's say the branch penalty, every time you see a branch, let's say there is no prediction for it, then every time I see a branch, then it is one cycle. Right? So now what is the speed up? The speed up is pipeline depth. You know that the pipeline depth, let's say for the MIPS pipeline stage that you were talking about, the pipeline depth was 5 divided by 1 plus pipeline stall cycles per instruction. We are not worried about, let's say we are not calculating the stall for any other, let's say we are not worried about whether there is a dependency of instruction, that's why there is a stall. We are not worried about it. Let's say we are worried only about the branch instructions. Then this is branch frequency into branch penalty, because the pipeline stall cycles from branch, I am just plugging it here. So it is 1 plus 0.33 into 1. So this is 5 divided by 1.33. Can anybody tell me what is the value of this? 5 divided by 1.33. How much is 5 divided by 1.33? Yeah.
3 point something.
Yeah, 3 point something, right? So it's, let's say 3.x. So you can see that the speed up was 5. Because there were branches, my speed up reduces to 3 point something. So that's why we are saying we have to reduce the pipeline stall cycles from branches. And the way to reduce pipeline stall cycles from branches is either reduce the branch frequency or reduce the branch penalty. Now, how can I reduce the branch frequency? I can't reduce it because this is the piece of code given to the hardware. As a hardware, I cannot reduce the branch frequency. The only way I can reduce the pipeline stall cycles from branches is by reducing the branch penalty. And how do I reduce the branch penalty? Maybe instead of multiplying this one, because I'm always adding 1 clock cycle delay or 1 clock cycle as a stall, but maybe if I have some kind of prediction, instead of 5 divided by 1.1 plus 0.33. I can't reduce this 0.33 because these are the branch frequency and this is the program that I am given. Maybe I will reduce the stalls on average per branch instruction to say 0.5, which means that I'm doing some kind of prediction. Now, can you tell me what will be the speed up? Can you tell me what will be the speed up? So this was 3.76. Sorry, 4.2. 4.2. So you came up with some stupid predictor, which is right only half the time. Right, you came up with some stupid predictor, and let's say there is no penalty for actually predicting wrong. Let's say there was no extra penalty for predicting something wrong. Then you came up with a stupid predictor which said that 50% of the time it is right. You are just tossing a coin. Maybe you gave a coin to the branch predictor and said, just toss a coin, predict something. Let's say I am right 50% of the time, then I am getting a better speed up, right? So instead of 3.76, I'm getting a speed up of 4.2. But if I build a 100% accurate predictor, let's say, okay, so let's say no prediction, right? So no, so let's say no branches in the instruction, speed up, just write down the speed up. The speed up is 5, right? Or say no penalty for branches. So let's say no penalty for branches. Somehow the pipeline is designed such a way that there's no penalty for this is not possible, but let's say that is possible. So the speed up is still 5 because I am just doing pipeline depth divided by 1 plus pipeline stall cycles per instruction for that particular branch. So for on average for the branches, so this will become 0. So pipeline speed up is nothing but the pipeline depth. Okay. So now we said that we have no prediction. We have no prediction, which means that I have 1 cycle stall per branch, right? And this is the instruction stream I have been given. So this is the instruction stream I have been given. So what will be the speed up? We already calculated that the speed up is 3.76. Okay. And then we said we will build some kind of prediction, and the prediction accuracy is 0.5, which means that it is right 50% of the time. We are not having any penalty for misprediction. So if I'm right, I don't have any stall. We already saw this. If I'm right, I don't have any stall. If I'm wrong, then I have a stall of 1 cycle. Right? So if that is the case, if the prediction is 50% right, so then the speed up is 4.2. Can you calculate if the prediction is 95%, which means that I am right 95% of the time, what will be the speed up? Can everybody try it out using a piece of pen and paper? My prediction is right 95% of the time, which means that only for 0.05% of the time I am paying a penalty. Can you tell me what will be the, try it out? But anyway, I'll leave it to you because I'll anyway be posting some questions. Let's say the prediction is, sorry?
4.91 something.
Yeah, 4.91 something, right? So, and if my prediction is 100%, which means that there is no penalty that I pay. If prediction is 100% right, equal to no penalty that I pay, right, then the speed up is 5. So just by building a very good predictor, I am able to increase the clock's IPC or the speed up drastically, right? So if something was taking, let's say something was taking 1 hour, without pipelining, something was taking say 5 hours. With pipelining, it had to take 1 hour, but it is no longer taking 1 hour because there is some penalty. So it means that maybe it is taking 2 hours. But then I came up with a good predictor. Then again I reduced it to 1 hour. So obviously you will buy a system which has a good predictor, right? So if I sell you a system, or if I sell you a processor without prediction, you might not buy it because I am not able to give you that speed up, which means that the processor is slow, which means that every application is slow, which means that you're not able to play games, or you are not able to do really well, use your system really well, right? So it means that you are really annoyed. So building good predictors is a interesting challenge. This has been beaten down to death by the past 3-4 decades, but there are people still coming up with innovations. It's not as simple as it sounds because there are complex prediction mechanisms that happen. So that's why I was just saying that That's why I stressed upon how the prediction. Of course, the other way to is reduce the branch frequency. The compiler can do it for you, but compiler is also limited by what it can do because there are other moving parts, which if I just keep unrolling the loop, there are other moving parts which will hit me, which we will see in the next, say, 10 or 15 classes. But the idea is that it's not as simple as it sounds, and it's all marketing, right? So if I build a processor which is giving me a speed up of 5, and somebody comes up and says that I don't want to build a complex processor, but I'm giving you a speed up of 3.76, maybe you will not buy it. So you will want something which is faster and faster and faster. And this branch becomes even more problematic in something called superscalar processors, which means that you are actually not fetching one instruction anymore. You are fetching more than one instruction. There's a way to do that. Those processors are called superscalar processors. Maybe at the end of this course, I will just introduce you to something called superscalar processors. But computer architecture course, we will start with superscalar processors, where this becomes even more a challenge to solve. Okay, I hope this is clear. If it is not clear, just think about it. It will get clear. Okay. So we were seeing there are dependencies in the instruction. We didn't actually formally talk about the dependencies or formally talk about the hazards or formally talk about the stalls. I'm just, of course, introducing you in the reverse way. And if you take a textbook, they would have formally introduced you. They would have formally introduced you to the formula and then started with how do I solve this. But we actually solve the solutions first. Now we are going back to saying, well, how can I formally define this, right? So there are different kinds of dependencies in the instructions. The one is called the data dependency. And I can divide the data dependency into two things. The one dependency is true dependency. The other is name dependency. We'll see each one with an example. And we also see something called control dependency. This you might have already guessed what is control dependency, right? It's just an instruction that is following a branch instruction. That's why there's a control dependency, because something is dependent on the control. We'll see the example for data dependency. You have already been seeing this, but we'll see it in further. Any program given to you will have dependencies which can be classified into something called hazards. So there are different types of hazards. There are data hazards. In the data hazards, there are different types of data hazards. Read after write hazard, write after read hazard, write after write hazard. And then there is control hazard. And there is structural hazard. So we'll see one example after the other. But this is how, given a program, I can classify into something called hazards, data hazards, control hazards, structural hazards. In the data hazards, there's a read after write hazard, write after read hazard, write after write hazard. So let's take an example. Let's take an example which says something like this: add So you can see that there is some kind of dependency. See, we can say that there is some kind of dependency. I2 is data dependent. I2 is data dependent on I1. So this is what I'm talking about, data dependency or the true dependency. I2 is data dependent on I1. Why do I say that? Because whatever I1 is producing is consumed by I2. So I2 is data dependent on I1. Of course, this need not be just one level hierarchy. There can be an instruction I3. There might be an instruction I3, which is again dependent on I2, right? So let's say it is something like this. So I2 is dependent on I1, I3 is dependent on I2. So I3 is, so these are all a chain of instruction dependencies. So I3 cannot execute before I1 executes because it cannot execute before I2 executes. So I have to wait for at least the values to be known for both I1 and I2 before actually I can execute an I3 instruction. So we say that I3, I2 are data dependent on I1. I3 is also data dependent on I2. So this is a read after write hazard. So I can read R1, I can read R1 only after R1 is written. So that's why it's called a read after write hazard. You should read only after the write happens. So that's why it's called a read after write hazard. It might be confusing if you are listening to it for the first time. A raw hazard is read after write hazard. You have to read after something has been written. Only after R1 has been updated with or written with, then you can read that value. So that's why it's a read after write hazard. It's a data dependency or a true dependency because there is no way I can solve this but to execute R2 plus R3, and then only I can figure out what's the value of I2. Right. So this is what we have been seeing. We have been seeing data dependency, a raw hazard or a data hazard. Whether whether this hazard will result in a stall or not is not dependent on the program. It is dependent on the pipeline or dependent on the architecture or dependent on the processor that you are running. It might result in a stall. It might not result in a stall. So hazards are with respect to a program. Stalls are with respect to an architecture. Whether that hazard will result in a stall, if it results in a stall, how many cycles it will stall is completely dictated by the way you build the pipeline. So now what is a write after read hazard? What is a write after read hazard? Let's say I have an instruction, something like this. Now there is no read after write hazard, which means that I2 need not wait for I1 to get to produce some value. I don't have to wait, but I cannot go ahead and execute I2 before I1 because there is something that is happening here. That is a write after read hazard. So I can write the value of R2 only after R2 has been consumed by I1. If I somehow go ahead and write the value of R2 before I1 has consumed, then it so happens that I1 will be consuming the value that is R4 plus R5, which should not happen. So there is this write after read hazard here. I can write this value only after R2 is read here. So this is a write after read hazard. Write after read hazards is not there in the MIPS pipeline. There's no way that you can come up with a hazard of this kind in the MIPS pipeline that you have been seeing. This thing appears only in pipelines which are built to which are aggressive pipelines where they allow some instructions to continue execution even though there are stalls. There's a very complex mechanism to do this. Again, this is part of computer architecture, but there's a complex mechanism to do this. So they allow some instructions to continue execution even though there are stalls. Then you might end up with a write after read hazard, which means that will again result in a stall. But in the pipeline stages that you are seeing, it's impossible for you to see impossible for a write after read hazard to result in a stall. Whether there is a write after read hazard or not, yes, there is a write after read hazard in this program, but in the MIPS pipeline, this will not definitely result in a stall. You don't have to do anything specific to do this. It just doesn't result in a stall. Then we said there is an hazard called write after write hazard. I hope you have guessed it by now. It's just this. This is a write after write hazard. Right. Why is it? Because I can write something to R1 only after instruction 1 has returned to R1. Right. So I can write something to R1. I2 can write something to R1 only after I1 has returned to R1. So this is a write after write hazard. Again, in the MIPS pipeline, this will not result in a stall. This is a hazard, but this will not result in a stall. But there are pipelines Of course, not. There are very rare such pipelines where the right after right hazard comes up are rare. Even in a single stage, in a single cycle pipelines. But the hazard is possible. Generally, the compiler is intelligent enough to remove such hazards, because you can clearly see here. Let's say this was my instruction stream. Let's say this was my instruction stream. Let's say it's add R1, R2, R3, subtract R4, R1, R5, and so now there are two hazards in this particular thing. So can anybody tell me what are the two hazards? One is what? What hazard do you see here?
So I1 and I2 are having read after write hazard.
Yeah, I1, I2 are read after write hazard. So this is a read after write hazard. But we also see one more hazard. What is that hazard?
I2 and I3 are having write after read.
Write hazard, right? So this is a write after write hazard, and this is a read after write hazard. Now, whether this hazard will result in a pipeline stall or not is dependent on the pipeline. So this is dependent on the pipeline. Now, the compiler, if you are the compiler, what will you do to remove the write after write hazard? Let's say I want to remove the write after write hazard. Let's say I am compiling for an architecture where the write after write hazard will result in a stall. Right? And I am the compiler, I know this information. How can I remove the write after write hazard in this instruction stream? Any answer is fine. The pipeline is intelligent enough to do this.
We can put some independent instructions in between.
You don't even have to do that. You can do something better, easier.
Sorry, can I change the register like
Yes,
R1
sir.
to something else?
Yes, you can do it. So why can't you do it? So I just change this to say R temporary register and R temporary register. That's it, right? And then there's no write after write hazard. So the compiler just looked at it and said, okay, this is the dumb piece of code that somebody has given me. I just optimized this. I mean, this is just an example I gave you. The compiler can do a lot more things. Even the hardware can do this. There is an algorithm to do this. It's a hardware implemented algorithm called Tomasulo's algorithm. It's a very beautiful algorithm, which you will again be seeing only in computer architecture course. I know I'm advertising computer architecture a lot, but it's one of the fascinating subjects. Where the hardware will actually detect something like this and squash the write after write hazard. If the compiler somehow missed it, maybe the compiler was sleeping because it was 9 a.m. The hardware will figure out, because it will never sleep. It will just say, okay, the compiler just slept off. It did not do its optimization, and I will do it, and it will do it. So there are so many checks. You can see the beauty of it, right? You write a program, you think that you are the smartest programmer, but there are so many such things, so many moving parts, both in the compiler and in the hardware, that are making your life far easier than what you can envision. Right? So yeah, this is how it works. The last hazard I want to see is a read after read hazard. Do you think such a hazard can exist? Can a read after read hazard exist? So is I1, I2 a read after read hazard?
So both can read from the same register. It won't be a problem.
Yeah. So read after read is not a hazard, because it is not a dependency. I can just have multiple ports or multiple places to access this register. Then there is no hazard. So read after read is not a hazard in any of the literature. So it's just that the data hazards are read after write hazard, write after read hazard, and write after write hazards. The read after write hazards in the mixed pipeline, you have been seeing that they might result in a stall, and you squash those stalls by something like doing some data forwarding. You might not be able to do data forwarding. In some instances, we saw that example also. So whether a hazard will result in a stall or not is dependent on the pipeline. There are other hazards called write after write and write after read, which will not result in a stall in mixed pipeline because of the way the pipeline is designed. But there are architectures where this can result in a stall, and there are ways to resolve these stalls. We'll see other hazards later in the class. I will stop the recording. But if there